Um, Good afternoon. Thank the organizers for inviting me to give this talk. And I'm going to talk about diffuse matter from CGM to IGM. If we look at the inventory of matter energy density in the universe, we find that just about 5% of it is in the form of baryons. But within that, a large fraction, about 90% of it, is in the form of diffuse gas. Some of it is in the form of Lyman alpha forest in the intergalactic medium, or warm hot intergalactic medium, and some of it is, so this part, for example, in the Lyman alpha forest and the WIM is in the intergalactic medium outside of any collapsed structure. And it's actually very interesting that most of the matter in the universe, baryonic matter in the universe, is outside of any collapsed structures. About, say about this, what's about 20% of it is in resides in collapsed structures. Some of it is in galaxy cluster halos, which we call the intercluster medium. Some of them is in galaxy halos, which we call circumgalactic medium. So it's very clear that the study of baryonic matter in the universe depends very strongly on, depends on how well we know its diffuse state. And what makes it difficult is that this matter exists in a wide range of density and temperature. And matter in different temperature ranges, for example, are detected in different manner. In some cases, for example, in CGM and in IGM, the density is so low that you can't detect them in emission. So you have to rely on absorption studies, which makes the interpretation of the physical condition of this gas very, very difficult. So I'll start with a CGM, and in particular the connection between the disk galaxy and the CGM, because that's something that I have been working on. The observational clues to the existence and the properties of the circumgalactic medium comes mainly from absorption studies, and a lot of it has been learned from the COS studies recently. So when the light from a distant background bright quasar passes through the outskirts of a galaxy halo, it intersects a part of the circumgalactic medium, CGM, and the absorption features can give clues to the properties of the CGM. For example, and there are absorption features lines which can tell you about gas at different temperatures. For example, O6 lines tells you about gas at few times 10 to the power 5 Kelvin, or SI2 lines, for example, gas at few times 10 to the power 4 Kelvin, etc., etc. But these lines, so you can model these lines to give you column density and the turbulent or thermal velocities along the line of sight. But what makes it difficult to convert these observables into physical parameters like density and temperature is that along the line of sight, the gas can exist in wide range of density and temperature and velocities. So usually one interprets them in terms of uniform observers. But then also there are problems of some lines are excited by collisional ionization, by photoionization, etc., etc. So all these uncertainties actually make the estimate of how much of a gas in different temperature beings are there in CGM, these estimates become very uncertain. So that's something to look forward to in the next decade, I suppose. But what is known, for example, if you look at the expected baryonic content in galaxy halos, and look at how much of it is in the form of stars, stellar remnants, and cold ISM in the disk, it's about 30% of the total baryonic content in a galaxy. That leaves out 70%. And one hopes that, it's in the form of, it's in the circumgalactic medium. So recently we looked at jointly the X-ray and stacked X-ray luminosity. Some galaxies have been seen in X-rays, CGM, and especially the central part. And you also expect Sunni Abzeltovich effect if it is hot enough. And so from these studies, we have been able to constrain some of the CGM properties of the hot CGM assuming very simple temperature structure, isothermal temperature, and we find that the hot phase at least has a density profile of about 1/r, and then it gives us, says that the warm hot component contains about 10% of the galactic baryon, so that adds 10% of it here. Rest of it could be in the form of warm, cold, warm phase, and there are observational indications for that. One doesn't know what is the physical state of this gas. One of the recent models, for example, says that it could be in the form of droplets of cold, warm gas with a large filling factor, just like a mist that we see in winter mornings. Now, there are observational indications that the properties of CGM, you may have seen this cartoon many, many times. This is from the annual review by Tomlinson last year. So one knows that the CGM property is somehow related to the star formation activity in the galaxy. So the questions that one can ask is, how much of this gas, the CGM gas, circumgalactic gas, is from the original gaseous content out of which the visible galaxy has formed, and how much of the disk gas has been thrown into the CGM. And so these are the questions one can ask. For example, what is the process of mixing? What are the energetics? What is the threshold star formation rate, or the density of star formation rate, for example, which is needed to throw up gas from the disk to the CGM, and so it's probably going to get recycled and spur star formation in the galaxy. So these are the questions one can ask. Recently, we have done, this is a paper from a paper we have just submitted earlier this month. We have done a series of tall box simulations of a stratified disk with this range of star formation rate densities, and this is increasing star formation rate density. This is density and temperature. And we have been able to identify a threshold star formation rate density, surface density, or which can be translated into energy injection density, which can throw gas into a few kiloparsecs above the disk. Of course, it depends on what is the phase of this gas. Is it cold gas, hot gas, etc., etc. I won't go into the details, but this is the sort of energy scale we think we get, about a few times 10 to the minus 4 ergs per second per centimeter square. And interestingly, this is also the energy scale that people have inferred from the studies of synchrotron halo, for example. When you look at edge-on star-forming galaxies, you see synchrotron halo, and then you can ask this question. If you look at a number of them, you can ask this question: what is the threshold star formation rate energy density that you need in order to have a synchrotron halo like this? And they also infer a similar energy density as we have. So this is very encouraging. But one can say that this is synchrotron radiation needs magnetic field. It's not just gas, so you need to have magnetic field thrown up. And so we are trying to do a. This is very, very preliminary. Please, don't take it with a grain of salt of this surface image, brightness image that we have produced with an MHD simulation of an edge-on star-forming galaxy, and we are trying to match the observations and try to understand what are the energetics that are necessary in order to create a synchrotron halo. Basically, the energetics for throwing disk gas into the CGM. Now, it looks like the most important underlying process of throwing the disk into the CGM is thermal pressure. And what is needed is star cluster, the more massive the better. And you need to have some sort of a coherency in supernovae rate, so that you have bubbles created by one supernovae, which is going to lose energy radiatively, but you need to keep pumping enough within a certain space and time to keep it blowing. And one can check with do observational checks with nearby starburst galaxy, and there are enough examples of this. In our own galaxy also provides us with interesting laboratory of the Fermi bubble. As you know, the gamma ray sky, you see two bubbles on the two sides of our disk in a few tens of GeV, and this can be understood with the energetics of star formation activity in the center, and can gas be thrown out to about 10 kiloparsec. This is in height, and then but one has to model the multi-wavelength emission. For example, this is in gamma ray. This is the simple hydrodynamical density contour of a Milky Way type galaxy. And we have seen this in gamma ray, X-ray, radio, so that this matching can help us to constrain the energetics, the time scales that are necessary to throw gas up into the CGM. This also tells us, so for example, looking at the X-ray emission from this gas which is being thrown out. This is hot gas. A lot of it is hot gas. But apart from the hot gas that is also there, this is the temperature map. There is hot gas here, but there's also hot gas in the CGM, in the Milky Way type galaxies, which can emit X-rays. So for example, this can explain, this is a plot of X-ray luminosity and surface star formation rate. And if the X-ray luminosity were to come from, X-ray emission were to come from only from the injected hot gas, then we would have expected a relation like this with star formation rate, but you don't. The data are scattered here. Even for low star formation rate, there seems to be a lot of X-ray emission, and we think this is because of hot CGM. Okay. Lest you should think that this throwing up of gas from the disk to the CGM is a local phenomena, has no cosmological significance. It may have far-reaching consequence. For example, as this gas is thrown up into the CGM, even to a few kiloparsecs height, this gas is going to cool because of thermal instability, and it's going to get perforated, and it's going to provide channels for ionizing radiation to escape. And that's exactly what is needed to reionize the universe, for example, at high redshift. But one usually takes the escape fraction of ionizing radiation as a free parameter, but one has to understand this in the form of, as a function of galaxy type, as a function of star formation rate, if possible. So we've done some preliminary studies on this, and we think the angle time average escape fraction of Milky Way type galaxy we get within about 5%, which is consistent. And this is sort of trying to understand on what are the parameters does the escape fraction depend. This is color-coded escape fraction. This is 50%, 5%. And this is scale height. This is the disk gas density. And Milky Way is somewhere here with a 5% escape fraction. But we're trying to understand on what does the escape fraction depend on, and can this be used in order to understand the process of, for example, reionization. So it has far-reaching implications, although it's a very local, small-scale phenomena. And it's becoming more and more clear that this, the dynamics of throwing gas into the disk-CGM connection depends a lot on the dynamics of superbubbles around OB associations, like, for example, 32 radars in LNC. And although I said thermal pressure is the most dominant process, one can also ask the question whether other non-thermal pressure, for example, radiation pressure, what about cosmic ray pressure? Are they important? And there have been claims and there have been studies of how cosmic ray can be important in putting gas into the CGM. We thought we'll study first its role in small scale, where there are observations, one can do observational checks in star clusters. So, for example, this is an example of a study with putting cosmic rays in a small star cluster, massive compact star cluster, and trying to, this is a simulated image from a 3D two-fluid model, simulated image in different wavelengths, with and without thermal conduction, all kinds of, and cosmic ray diffusion put in. Basically, we have tried to understand, we think we understand by looking at gamma ray, X-ray, radio observations and checking with the star cluster, is that the cosmic rays are probably accelerated in the Wien termination shocks. And this has actually taken us to unexpected avenues into understanding cosmic ray acceleration, but that's not the story for this conference. So this is all we know about putting the CGM, the disk-CGM connection. What about CGM to IGM connection? This gas which is being thrown out into the CGM has to at some point come out of the CGM, which, if, say, for example, for Milky Way type galaxy, the virial radius is about 250 kiloparsecs. And all of this is filled up with a lot of matter, if it is filled up with the missing galactic baryons. And so this is an example of a simulation of, it's a high star formation rate, it's about 50 solar mass per year from a Milky Way type galaxy, being continuously injected energy and mass, and how this outflow is going to plow through the CGM and reach the virial radius, and if possible, will go on to the intergalactic medium. And one has to understand this. There are problems with this because we find that the speed of the outflow becomes very, very small. There is almost like sonic speed of the hot CGM. And, but there are problems also to do with what is the mass loading factor, for example. And why is it important? Because the CGM, the intergalactic medium is not pristine. There are metals that are known from the studies of absorption studies. And well, it has been known for a long time that one can explain the enrichment of the intergalactic medium from winds of galaxies, especially from low mass galaxies, small galaxies, which have shallow gravitational potential, so it's easy to excite winds, and they were numerous at early galaxy universe. And although the metallicity is low at, for example, very low, 10⁻³ or lower at redshift of 3, one has to explain the IJ metallicity, and people have shown that, in the many studies that it is possible to do that. But when you do simulations and try to match, for example, this is at high redshift, this is at low redshift, and galaxies and the metal density, and people try to match this with, in cosmological simulation, you use subgrid physics, and because you can't resolve out physics, and the subgrid physics depend on outflow models or from what is known from outflows at very small scale, at 10 kiloparsec level. And for example, this is a recent paper in Archive which brought out that there is a tension between what is required from cosmological models of enrichment of IGM and what is known from outflows at 10 kiloparsec level. So one has to bridge this gap of CGM to IGM and what is known, for example, 10 kiloparsec level to 250 kiloparsec level and beyond. And that's something, again, to look forward to in the next decade. Another interesting effect, a physical effect in the CGM-IGM interface could be because of cosmic rays. It's been known for some time that cosmic ray protons can heat up IGM gas, and recently it has been shown that it can be important for high redshift mini halos undergoing starburst, and it may lead to global heating, which may have implications for 21 centimeter observations. Recently, we looked at the effect of CR cosmic ray diffusion, which tells us that the temperature profile can be steep, although it will be in such a small angular scale that it will be difficult to observe. But the heating due to cosmic rays at or beyond the virial radius, in some cases, even at low redshift, may be important for sort of a negative feedback for gas infall. Now, I'll stop with IGM. So, about 30% of it is in the form of Lyman alpha forest. It is photoionized, heated by UV background, and they adiabatically cool. So the expected equation of state is goes like this, which has been, so this is a balance between heating, photo heating, and adiabatic cooling. But there is a huge fraction of the intergalactic medium which is in the form of warm, hot, or hot intergalactic medium. So 10 to the power 5 and beyond, 10 to the power 6 and beyond, which there are observational clues from the studies of 06, 07, 07, 08. So a number of years ago, I also tried to calculate the equation of state for this warm, hot intergalactic medium taking clues from the 1972 paper by Sunyaev Zeldovich. Basically, it's shock-heated because of structure formation. And one of the interesting predictions that we made is that the integrated Sunyaev Zeldovich distortion from the warm hot intergalactic medium could be of the order of 10 to the minus 6, which is very, very small. But again, something in the next decade, this may be detected. So I'll stop here. And to say that, study of the diffuse matter is important to study, to understand large-scale structure evolution. And in addition to cosmological box simulation, I think it is also important to idealize small-scale evolution where you can do controlled experiments. And of course, I'm sure there will be inputs from new observational tools, which will help. Thank you.
Thank you. We have plenty of time for questions.
Radiation pressure that many groups consider fundamental is less important than thermal pressure, and if this is going to be true also in a starburst galaxy in a more gas-rich environment.
Yes, and especially if there's dust. So in star clusters, it is important in the very small scale when the star clusters are young. But if you have dust in the disk, for example, and there is enough star formation rate, then the dust can be elevated, and the dust can actually drag along the gas because of Coulomb dragging, because the dust's grains are charged. And it can be important. And I think there are some observational inputs. In fact, this paper that I mentioned in arXiv, which brings out, they talk about this, the radiation pressure. It can be important, yes.
If there is no more questions, then let's thank Biman.